Okay, so as usual, lots to cover today. We'll see how far we get. We may not get to the Doppler shift and all that stuff. I always cover Doppler shift in this class because it shows up on the MCAT all the time, so students always want to know about that. That's all. And it usually shows up on the final too. But we'll have a lot of, so today's going to be about waves, and I'll try to relate it to oscillations. We talked about a lot last week. Real quick at the beginning, now I'm just going to put this thing. Oh, I put it on. Let's see. Can I get the power? Is that going to work? You're going to give me power? Well, here, I just wanted to show you what the histogram looks like for the second midterm, if I can get it to go. Get it? We can only do it? Oh. I'm not convinced. I can see it up here, but I don't see it up on the big screen. Switch what? All right. So now I'm getting this. Let's see. Sorry. Oh, so now you can see this. So that's my voice there. You can see me talking, which you've always wanted. But where's the, how do I switch it to the Elmo? There must be some trick to put it on the Elmo. Can I do that? Oh. Switch it back to main? All right, back to main. And then I'll go back the other way after we do this. Is it working? It's working. Oh, wrong class. That's us right there. So, I don't know if you can see it. I can barely see it myself. The bottom line is that the mean is around 75, standard deviation around 19, standard 20. So you did, as a class, you did, the scores were a little stronger on the second midterm than the first midterm, which is good. Partially, I think that it was still a pretty challenging exam. This was a pretty tough exam, but people did pretty well. Just so you have an idea what the spread looks like. Again, if you're concerned about your grade, we're talking about office hours. Finals were 40%, so there's still a lot of points to come. And some of the stuff that's going to be on there is on stuff we covered last week, and it's on YouTube, so you can go check it out if you missed the lecture last week. Okay, anyway, just to give you an idea where we're at with that. A little more than the first exam, people got piled up at the top a little bit. I think we're doing a pretty good job of separating out the A's and the B's. But anyway, so I think for the final, the difficulty level's going to be somewhere, this is about right. The second midterm is about what I'm shooting for to sort of separate people out and you get a chance to show me what you know. Okay, so now I'm going to go back to, I'm going to hit this button here. I'm going to go back to having to put the camera back down here where I am. And we'll do a little bit on the board before we pick up the microphone. So, all right, we talked about oscillations last time. And I'm going to distinguish oscillations from waves. Students often ask, what's the difference in oscillation and a wave? Well, first of all, sort of remind you, we got oscillators. The canonical oscillator is a mass on the end of a spring. The spring has some spring constant K. The mass on the end of the spring has, some mass M, right? And we worked out what the frequency of oscillation is for that thing, right? So now it's going to go like the square root of K over M. Okay, great. I mean, we thought about that and why that made sense. Bigger K means bigger oscillation, bigger M is slow down, it's lower oscillation sort of makes sense. Real quick, let me point this out. So we've seen now many ways to think about the same problem. Suppose you're asked a question about, I don't know, Tarzan's up on a branch. I want to draw an elaborate picture of Tarzan. Here he's up on a branch. He's going to swing down to his friend, his monkey friend or whatever. I don't know. Okay, so there's a monkey buddy. He's going to get down here. How long will it take him to do that? To swing down like that? Well, there's lots of ways we thought about solving this sort of problem. We have lots of tools now, right? You might think, well, I can use Newton's second law, right? That's F equals ma. So F equals ma could get you there. You could use that, but it's a pretty complicated set of integrals you have to do. It's beyond the scope of the class. It's all the nasty set of integrals you have to do to actually figure out how long it would take them to do that. But we also have conservation of energy, right? It's another way to think about this problem. Well, that might be useful if we know how fast he's going to go at the bottom, right? Because then we know, we'll just do mgh, which is, if this is h, right? And say, we want to relate that to how fast he's going at the bottom, 1/2 mv squared, which is the velocity at the bottom, and then masses cancel. So that allows us to solve something. But it wouldn't tell us in a convenient way, without doing more work on top of that, it wouldn't tell us how long it takes. What else we learned about? We learned about conservation momentum, right? The problem with using conservation momentum in a problem like this is that you have to work out the impulse due to gravity. Actually, due to gravity and the tension inside this rope he's hanging on, right? So you can do it, but again, it's a complicated set of integrals you have to do and all that. So this might be useful for solving some other aspects of the problem, but not for how long it takes in a convenient way. We also learned about Newton's second law for rotations, and that's where we're getting close now, because now we can write this, tau net equals I alpha. I easy to calculate. He's a point like mass, and so on. We worked out though that if we try to solve this thing exactly in this case, it turns out to be sort of nasty. But if we take this idea and then use small angle approximation, right? So we're getting a recap of a bunch of things we've done to put it all in perspective in one problem. Small angle approximation allows us to substitute sine theta for theta, right? So sine theta is about equal to theta. By theta, I mean this angle. And then we found, we can think of this as an oscillator, simple harmonic motion, simple harmonic oscillator. Well, we can solve that. Then we know what the frequency of oscillation is for this thing. It's different than that formula, right? We worked it out for the case of a pendulum. It's just a pendulum, right? It's going to be what? I know it goes like G and it goes like L. I think G goes on top, right? Because the bigger G is, the faster, the bigger L is, the slower. That makes sense. So once you know what the oscillation frequency is, then how could you figure out how much time? So compared to a period of oscillation, how much time is it going to take for him to get from the branch down to the bottom? Half a period? What do you think? Is it half a period? So what does a period mean? Period is a full oscillation. So that means he starts up here, he swings down, swings up over here, comes all the way back to where he started from. So it's not a half a period. What is it? It's a quarter of a period. That's right. So if you want to know time to bottom, right? It's equal to, we use capital T for period. Of course, capital T could also be tension in the rope, so be careful. Period over 4. And we say, how do you relate that to omega? Oh yeah, the period is just, let's see. I have to think about it. So there's all those equations to relate all the different aspects of an oscillation. But the period is what? It's in terms of omega. Well, it's got to be like 1 over omega, right? Because you have, this is seconds, this is 1 over seconds. But then there's going to get 2 pi floating around. Well, let's see. I know this is equal to 1 over f. F is the frequency as measured in terms of the number of cycles per second, right? Cycles per second. Well, omega is the number of radians per second, right? Are there more than 1 radians per oscillation? Or less than 1 radian per oscillation? Well, how many radians is a full oscillation? You go all the way around a circle. You go all the way there and back. 2 pi. There's more than 1. So yeah, so it's 2 pi f equals omega. The 2 pi goes over here. Because this is a bigger number than that is for a given oscillator, right? Because there's more than 1 radian per full cycle. Okay, great. So once I know that, I say, if I have an f down here, that means the 2 pi I think has to go up here. Is that right, everybody? I think that's right. It says that 1 over omega goes like 1 over 2 pi f. 2 pi. Yeah. Anyway, so this is what you would do. You substitute it over here and you solve it. So ultimately, how much time is it going to take? Of all the different approaches we've seen, it's the oscillator approach that's going to solve that problem the easy way for you. So just keep in mind, you have lots of tools at your disposal now to look at the same problem, whatever that problem is. Anyway, I just thought I'd bring that stuff up and remind you of some of these relationships with oscillators. So now what about waves? If you've got a wave, what's the difference between a wave and an oscillation? Well, a wave is some phenomenon that takes energy from one place to another without the stuff itself, without any matter going from the one place to the other. What do I mean by that? If I have, no stick? Oh, no stick. I'll use this little xylophone stick. Here we go. All right, this won't be very big though. So I want to make a wave on this rope. So I got a rope that goes across the classroom. I'm going to whack it in one spot, and it's going to cause a wave, and the wave is going to move that way down the rope, right? So sure enough, right? I know, very exciting. Surprise and a wave for you. But here it goes. I'll do it again. So there's a wave. It's so fast, actually, that it may be a little hard to see what's going on. It starts to wiggle like crazy, and waves are going in all directions. But what I'm trying to do is make a very local disturbance in this rope, so that you see a well-defined wave crest going down the rope. So I'll do it one more time. It's pretty quick. It goes there and back in less than a second, right? So it's moving pretty fast. So the idea is that the rope itself is only wiggling up and down, right? If I put a little piece of tape on this piece of the rope, that piece of tape didn't zoom down there and back. The rope's not going that way, but the wave's going that way. So that's a typical characteristic of a wave. There's a bunch of oscillators. This rope you can think of as a series of coupled oscillators. There's lots of little pieces that are oscillating, in this case up and down. There's other kind of waves too, but in this case it's a transverse wave. A wave where the oscillations are perpendicular to the direction of motion of the wave. So I'm wiggling this little piece of rope up and down. As a result, a wave propagates out, and the rope itself doesn't move in that direction, just the wave does. So that's a wave. You have to have oscillators around of some kind to produce a wave. So you need oscillators to produce a wave. But if you don't have a bunch of coupled oscillators, you don't get a wave. You just might have an oscillator by itself. Like a mass and a spring can oscillate. But I want to sort of give you a wave. Let's couple a bunch of them together. So let's think about transverse waves and longitudinal waves. So I just told you that was a longitudinal wave. So it looks like this. I'll describe the rope this way. I'll describe it as a bunch of masses. This is not an ideal rope. It's a rope that's got some mass. Right? It's also not inextensible. It actually stretches a little bit. So what I'm going to do is I'm going to draw a bunch of masses and put springs between them and use that as my model for the rope. And say, all right, what's a simple picture of what a transverse wave looks like? Well, it kind of looks like this. So at one moment, I'm drawing right now is one moment in time. I'm drawing what the rope looks like. So here's a bunch of masses. Each one's got the same mass m, and then there's these springs, and they have some spring constant, whatever it is. And it looks like that. So at this moment in time, I've got some wave that looks like this. A few moments later, some later time, it might look the other way. This mass that was a little bit higher than the average height for all the masses, now it's a little bit lower. And this guy over here used to be low, now he's going to be high. Right? So it'll look like this. So in alternate moments in time, right, the masses are wiggling up and down, and neighbors are a little bit out of phase, right? This guy is out of phase exactly 180 degrees out of phase, or pi out of phase from this guy. So when he's up, he's down. When he's down, he's up, right? And when this guy's up, you can see what's to make him, what restoring force, what's to bring him back down. It's the fact that his neighbors are down, pulling down on him is what makes him go back. So you have a bunch of coupled oscillators, and if I wiggle something over here, it'll propagate down. And that's a transverse wave because the oscillations are in the vertical direction, but the wave, the direction the wave is moving is in the horizontal direction. So that's a transverse wave. You can also have longitudinal waves. So a longitudinal wave looks like this. I can take the same object, although it's harder to demonstrate by me wiggling the rope to be able to see it very well. But you can take the same thing, which is a bunch of masses or springs between them, and now wiggle them back and forth. And you can have a wave that propagates that way, even though what's going on is that the oscillations themselves are going that way. So here's the same object. Now I crunch these two masses close together. I spread these two out. I crunch these two really close together. I spread these far apart, right? And so on. So here's one moment in time. And now the next moment in time, these guys are far apart. So this spring, which was crunched up here, now it's spread out at some later moment in time. Now this guy, you get the idea. So it does this. So this is an example of a longitudinal wave. That's a wave that, for which all the oscillators that are coupled together and they're allowing the wave to occur. The medium along which the wave propagates, right, made up of these masses and springs. The oscillators are all moving in the direction that the actual wave moves, right? Now the kind of wave that most of us think of, I think when we first think wave, we think ocean waves, right? Ocean waves are sort of a complicated hybrid of these two types of waves, and so we won't do too much math with ocean waves just because it's actually kind of complicated. But in terms of the description of the wave, the surface of the ocean, the math's all the same. So we will talk about the sinusoidal shape of a wave and how it's moving. We'll do that in a few minutes. When we do that, it won't matter whether we're talking about a longitudinal wave or a transverse wave. All that math is the same. But when we talk about the physics underlying what causes the wave to occur, right? Which I'm not going to sad to hear. I'm not going to go into derivations in class. The book has a few derivations about exactly why the wave speed is what it is in a rope, or how you calculate the power, things like that. I'm not going to go through those derivations in class. But when it comes to water waves, those derivations are yet more complicated. They aren't even in the book, right? It's just more involved. It turns out that way. So there's two extreme kinds of waves, transverse and longitudinal, and then there's other things that are in between. And just to be clear what I mean by that, if you were to look at a little test volume of water, maybe take a little piece of plastic and put it inside the wave. Maybe it doesn't float. Maybe it has the same density as the water, a little baggie of water in it, right? And put it inside the wave and see what its motion looks like. If the waves are going toward the shore and the shore is over there and the surface looks like this, moving along, what you'd see is that the little piece of water sort of goes in a circle. So it goes a little bit longitudinally and a little bit transverse to the direction of the wave. But these are the canonical sort of waves we'll focus on. All right, and so the example I gave over here with the rope was a transverse. Sound waves are a good example, or a common example of longitudinal waves, right? Because the way sound propagates across the room, I'm amplified right here, so there's some speaker up here. But if you forget about the speaker, if I were speaking here, right, and sound's coming from my mouth and coming to your ears, how does that happen? Well, what's happening is there's vibrations going on in all kinds of complicated ways, and the result is that the air pressure right near my mouth goes up because I push a bunch of air molecules that way, and they cram up against the ones that are outside my mouth. So there's a slight increase in the air pressure just outside my mouth, right? And then as a result, it winds up pushing those air molecules that way and crunching over here, but then it gets rarefied right here. So the pressure goes a little bit below the ambient pressure in the room momentarily after it was momentarily high, and you can make the same kind of pictures of waves. But what you're plotting on the vertical axis then isn't displacement in the vertical direction of the rope, say. What you're plotting is the pressure, the air pressure in some place in the room at some moment in time. So when we talk about oscillators, right, we were able to think about, we drew these sine waves, but it was always, the position of the mass as a function of time, or the velocity of the mass as a function of time, or the acceleration of the mass as a function of time, maybe its energy as a function of time, but it was always time along the horizontal axis. Now when we have waves, we got more variables in the problem, right? Like for this rope, there's the y direction, there's the x direction, and we've got time. And so we should be really careful about our axis labels, as we should always do anyway, but we might mean two different things with a very similar looking picture. So let's draw a picture now of a wave. And again, it doesn't matter if you think of it as air pressure, or if you think of it as voltage, or we think of it as position. But let's just think, for the sake of argument, I'll call it y, and I'll think of y as the vertical direction looking at this rope. And what I'm plotting is going to be some wave at some moment in time. So this will be x. This will be my horizontal direction. Okay, so space versus space. It's a snapshot, in other words, of the wave at one moment in time. There's lots of different wave shapes I can make. In fact, the wave shape I was making over there, I was trying to make a little pulse, an upward pulse that propagated down. But to keep things simple right now, let's just think about it in terms of sine wave. So I've got some sinusoidal shape. It goes through, let's see, I almost said it goes through a period, but it's not a period here because this isn't time, it's x. So we're going to call this thing a wavelength. That's one wavelength. Now, as I always lament in this class, and in all physics classes, we don't have enough letters to go around, so we call wavelength lambda, even though we use lambda to mean linear mass density in a previous lecture. But lambda is very often used, and the book uses it to mean wavelength in the wave section of a physics text. So if this is x equals 0 right here, that's one wavelength. That's how far you have to go to get to the end of one oscillation in your wave in space. Okay? And the height of the wave is the same as it would be if it were in time, or it doesn't matter if it's time on the horizontal axis or x. In both cases, the amplitude is going to be the same, right? So we'll call that a, and we can think down here. All right, if we decided to make 0 the average value of the height of the rope. So if we go down here, this is going to be minus a. It's our amplitude. If we think of the y-axis as the displacement of some piece of the rope in the vertical direction, then that means a is going to be in units of meters in this case. But if this were sound pressure level or something else, voltage, you're going to have different units. The units just have to agree with whatever it is whatever the dimension is along which this thing's oscillators are moving. Right? Okay, good. So there's my snapshot. Let's say that's at t equals 0. That's just at one moment in time. Now, if the wave is propagating in that direction to the right, that means if I look at the picture later on, if I take another snapshot a little bit later, the wave's going to have moved over. So this part of the wave used to be right here. Now let's make it right here. What is that? Let's make it right here. 1/8. So this is what? Lambda over 8. 1/8 of a full cycle. So if I come down right here and say, all right, let's have the wave move over that far. So now it's done this. Right? Sort of gets chopped off now at lambda. Doesn't quite make it back to the axis because it moved over a little bit. Comes down like this. All right, here's my lambda over 8. Okay, great. So it's the same picture. I just moved it over. It's got the same height, same amplitude, everything's the same. I label the axis, so you know what I'm drawing. Okay. So how do I describe this mathematically with one equation that deals with both the shape in the x direction, right, y versus x, but also captures the time aspect of this. So it's the same thing we had before, but with one latitude peaks. You'd say that y as a function now of x and t, right, is just going to be, well, some amplitude. And in this case, what was it? It was a sine wave. So and there's no phase, there's no phi needed. We could add that on if we wanted. But I chose a simple example where it starts right at 0. So this is a sine wave. And what does it do? It's got kx. Oh yeah, I should describe what k is. And it's going to have to be minus omega t. So that's the equation that describes what I'm drawing right here. And let's think through how to relate these various quantities, and let's talk about what they all are. You've already seen omega and t in the context of oscillators, right? Same thing. This is just the frequency of oscillation of that little piece of the rope that's wiggling up and down at some particular value of x. But what about this k over here? So this k, I'm sorry to tell you, is not the same as the k. It's not the same as the spring constant. So like the k in that formula up there is different than this. Maybe when I use k for spring constant, I said, I like subscript. Just try to put sp for spring or something. Whereas what I mean by this k, when I've got a wave equation, what I mean by this k is the wave number. It's called wave number. It plays the same role that frequency does for time. And you can see what units it must have, right? Whenever you have a sine function or cosine function or exponential, whatever it is, the argument of those things, by argument I mean the thing that's inside the parentheses, right, has to be unitless. Omega is going to have units of 1 over time. So when you multiply by time, it means it's got no units. Same thing here, right? X has units of meters. It's a distance. This better be 1 over distance. And it is. The wave number has units of 1 over distance. Not the same as the spring constant, which has units of whatever, it's force over distance. So just keep that straight. And you can see also, remember that when we look at the comparison, when we compare omega, this omega here, and f, meaning frequency, the number of cycles per second, you get that nasty 2, well, I shouldn't say nasty, but you get that pesky 2 pi that keeps coming in, right? Well, the same thing is true for k, right? Because it's inside the argument of a sine wave. This thing, when this equals 2 pi, when k times x equals 2 pi, that means x has gotten to the point where sine has gone through a full cycle. So let's consider this picture right here. All right, so I got this one picture right here. I label it t equals 0. All right, well then look at our equation right here. If this equation is true, and I stick in t equals 0, then this goes away. So I just have a times sine of kx. What I want to do right now is relate k, the wave number, to lambda, the wavelength. So the way I do it is I say, all right, t equals 0, stick in 0. This thing had better equal 2 pi when I've gotten to this part of the curve, right? Started at 0, x is bigger. At some point I hit the same point I started at. And I don't just mean the same value in the vertical direction, the same value of the function and the same slope. Going downward here, it's got to go upward, be back in the same part of the cycle. So all the way out to here, that equals 2 pi. All right, 2 pi then had better equal k times the value of x when you make one wavelength. That's lambda. So that equation tells me how to relate lambda and k. Does that make sense? It's just like the same old thing I did already when I was trying to figure out how to relate omega and not little t, but big T, right? Because when I made the drawing of x versus t for an oscillator, I said, well, I know that omega times capital T, where this is intention, it's period, right? That has to equal 2 pi. This is the same idea, right? So one cycle, 2 pi, right? And that corresponds to this. Great, so now I know how to relate. If I want to know what k is, and I already know what lambda is, I'd say, oh, k just equals 2 pi over lambda, right? And you can read off lambda from a picture like this. It's just the wavelength, just how far you have to go in distance to get back to the same part of the oscillation again. And I could have measured it from any part of the wave. I could have taken it from a crest to a crest, or a trough to a trough, right? This thing is repeating, and we go up here, and that would be the same distance. Okay, great. So now how about this motion in time? So when I went from here to here, the wave moved over a little bit, but it's the same shape. It's the same exact shape in x, it's just that it's shifted over. So what's going on then, and I started at the beginning, I better put a minus sign in here, so why is that? Well, let's check to make sure this makes sense. If it's some small positive time later, right, so what time is it? Let's figure out what time it is. If it's some later time, see if that makes it go to the right. It's going to wind up being right for the same reason that last time we figured out, if you put a minus phi in, that results in a minus, I should say a negative phase added on inside your sine wave. That moved everything to the right a little bit. Remember that? And if I added a positive number inside my sine wave, it moved it to the left. Because the stuff that was already there had to take on the opposite sign in order to compensate for the thing added. So if you add a negative piece over here, this has to be more positive to get to where you were before. So this thing right here that used to be at 0, that moves to the right to give you a little bit of a positive x. It's multiplied by k to cancel out the little negative thing you added.